All right. Let me ask you all. Did any of your classes cover Newton's law of cooling? Fine, you didn't. I'm just making sure I would talk about it if we needed to, but I feel like we probably don't need to because it's more of a next quarter kind of thing actually. Yeah. We can certainly come back to it if we need to. So today what we're going to talk about is the derivatives of logarithms and the logarithmic differentiation that many of you will probably see on your exams on Monday or Friday of next week. So let's talk about that. And then depending on how long that takes us, after that, we can then, if you have any questions about any practice exams, also I should point out, I posted both classes, Zhao's and Alameda's practice exams on Canvas. I also posted another practice midterm too from Dedel and the solution, and then another practice exam from Alameda from I think last year. But I haven't posted the solutions yet, so I'll post the solutions that at some point. All right. As usual, if you have questions, feel free to ask them. So let's talk about the derivatives of logarithmic functions. So if our function is f of x equal to the natural log of x, and we want to find its derivative, you could do it, although it takes some work using limit definition, but we're not going to. So I'll just point out, we won't do this. The derivative is equal to the limit as h approaches 0 of the natural log of x plus h minus the natural log of x all over h. Although it certainly, with some extra information, is possible to do it this way. But we're going to do it a different way. So here's what we're going to say instead. We're going to say, great, I'm going to use y to the f of x. So we're going to start with y equal to the natural log of x. And then we're going to rewrite it in a way so it looks like a function we know how to differentiate. Specifically, we're going to undo the logarithm with an e to the power of. So we're going to rewrite this as e to the power of y equal to e to the natural log of x. And then the e to the natural log of x is just x. So we have e to the y equal to x. And now we're going to take the derivative of both sides of this equation, remembering that and seeing that y is a function of x. So we're going to use implicit differentiation to take the derivative of both sides here. The left-hand side is the part that's actually complicated a bit. So if we differentiate both sides, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. On the other side, the derivative of x is just 1. And then, just like every other time we use implicit differentiation to find the derivative, then we have to do some algebraic work to find the derivative. In this case, it's not too bad. We're just going to divide both sides by e to the y. Think that dy dx is equal to 1 over e to the y. Most of the time, this is where we'd stop, because our derivative would be isolated and be in terms of x's and y's. But in this kind of example where you start off with y actually as a function of x, we can then end by rewriting it as a function of just x. So notably, e to the y is equal to x. So we can just replace the e to the y, I should say the 1 over e to the y, with a 1 over x. So to make a long story short, the derivative of the natural log of x is equal to 1 over x. And with maybe one tiny exception, that's kind of the last type of function we learned about how to take the derivative of. So now we know how to differentiate just about everything we're ever going to see in this class. Powers of x, trig functions, e to the x, log of x. I think that's about it. I don't think there's any other types of things we learn how to differentiate. Oh, I should say e to the x and then any constant to the x, right? Like a 2 to the x or 3 to the x or a 5 to the x. We talked about that as well. And then, of course, we have the chain rule version. If the derivative of the natural log of x is 1 over x, then the derivative of the natural log of some stuff should end up being 1 over the stuff. But then what do we have to multiply by? always the derivative of the stuff. I should mention that's true even if your stuff is x. Because if your stuff is x, what's the derivative of your stuff? It's just 1. So you're always multiplying by the derivative of the inside stuff. It's just a lot of the time that inside stuff has a derivative that is 1. Let's do a couple examples. Let's say we want to find for f of x equal to the natural log of x to the 4th plus 7x. We want to find the derivative. In fact, you all should find the derivative. So I'll give you a minute. Oh yeah, question.
Can you roll derivative of like a constant?
Yes. In fact, we're definitely. I'm going to not quite immediately because we're actually going to circle back around to that pretty soon because I want to show you another way of seeing it. But yes, definitely we'll get to that again today. Good question. Thank you. Okay, so just applying the chain rule version of the logarithmic differentiation, I should say the derivative of a logarithm, because logarithmic differentiation is kind of a different thing, although related. It's going to be 1 over my stuff times the derivative of the stuff, and the derivative of x to the 4th plus 7x is 4x cubed plus 7. I choose to write it like this to remind myself that I have done the chain rule, but many people prefer to write it as 4x cubed plus 7 over x to the 4th plus 7x. Either way is totally legitimate and acceptable. Do what you want. Let's look at some more examples. Let's say our function is y equal to the natural log of sine of x. Let's find the derivative together. So the derivative, dy dx, or if you prefer y prime, same pattern. It's going to be, I have the derivative of the natural log of stuff. My derivative is going to be 1 over the stuff times the derivative of the stuff. And although most of the time I'm not too concerned with simplifying, here I actually do want to simplify this because I want you to see something. What's another name for cosine of x divided by sine of x? Is it cotangent of x? Yes, it is. Here's why I point this out. Next quarter, or whenever you take 17B and you learn about antiderivatives and integral calculus, we're going to care about finding the antiderivative of a function. So since the derivative of the natural log of sine of x is equal to cotangent of x, the antiderivative of cotangent of x is equal to the natural log of sine of x. We'll see that later, but just it's kind of to help you kind of warm up to the idea of, okay, antiderivatives, you're just going backwards. You're saying, what function would I have taken the derivative of to get the thing I'm starting with? Yeah, that's for next quarter, but I'm just trying to like make you aware it's coming up in your future or whenever you take 17B. Let's see, let's look at one more. So this is kind of my favorite type of terrible question here. Let's say our function is the natural log of something really extremely gross. X to the 5th times e to the 3x over, sure, tangent to the 4th of x times the square root of x squared plus 2. Okay, so if you see something like this on an exam, which you might, the intention is not for you to just throw the rule at it like we just did. Right? Yeah, you could. I've seen students do it the hard way, where they do 1 over all this stuff, and then they do the derivative of all this quotient, which requires the quotient rule and the product rule for the top and the bottom and the chain rule. It's terrible. You definitely do not want to do this. And people try to make this look extra daunting to remind you that you can simplify this expression first. We can use rules of logarithms to make this much nicer to take the derivative of. So I'll say again, it's almost always a good idea to, if you can, simplify the thing you're differentiating before you actually take the derivative. We don't so much care about afterwards, usually, but before, almost always a good idea. So here we're going to rewrite f of x as the natural log of the top part, x to the fifth times e to the 3x, minus the natural log of the bottom part, tangent to the fourth of x. And then I'm going to change the square root of x squared plus 2 to x squared plus 2 to the 1/2 power. Okay, now we're going to break it apart further. So just like the natural log of a quotient is the natural log of the top minus the natural log of the bottom, the natural log of a product, x to the fifth times e to the 3x, is going to be the natural log of x to the fifth plus the natural log of e to the e to the 3x. Same thing over here. We're going to get minus the natural log of tangent to the fourth of x plus the natural log of x squared plus 2 to the 1/2 power. And then there's one more simplification we can make before we actually take the derivative here. And that final simplification is if you have something to a power in a logarithm, that power can come down in front of your logarithm. So we can rewrite this as f of x equal to 5 times natural log of x plus 3x times natural log of e. I'll remind you that natural log of e is 1. That's not going to really matter. Minus, the minus sign is going to distribute to both these terms. So it's going to be minus 4 times the natural log of tangent of x minus 1/2 times the natural log of x squared plus 2. This x squared, that power there cannot come down in front because it's not the power on the entire thing we're taking the logarithm of. So it has to be the power on the whole expression, not just a piece of it. One thing I would point out, this is always true, whenever you do this process, the factors on the top end up with positive logarithms, and the factors on the bottom end up with negative logarithms. So it's positive natural log of x to the fifth plus natural log of e to the 3x minus natural log of tangent to the fourth minus natural log of x squared plus 2 to the 1/2. And then you can bring down the power. So you kind of skip this intermediate step here and go straight to like here and then here. And now, finally, we're ready to take the derivative of this much less terrible expression. It's still terrible, it's less terrible. So now our derivative is going to be, let's see, the 5 hangs out. The derivative of the natural log of x is 1 over x. Plus the derivative of 3x is just 3. Minus the 4 hangs out. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is the derivative of tangent of x is secant squared of x. Finally, minus 1/2 times the derivative of the natural log of that stuff is 1 over the stuff, x squared plus 2, times the derivative of the stuff, which is 2x plus 0, which is 2x. And although there are some small simplifications we can do, bless you, I wouldn't take the time to do them unless specifically instructed to on an exam. This is a perfectly good answer. I would leave it like this. So I'll say it again, especially if you see a log of some gross product quotient kind of thing, it's almost always in your interest to expand it out into simpler logarithms and then take the derivative of that. Yes.
Why did the 1/2 negative?
So I brought this 1/2 down in front, but the minus sign here distributed to both that and that. And so I will say again, I kind of wrote more steps than I usually would here. I would normally just jump straight to the step where it's plus natural log of the top thing, plus natural log of the top thing, minus natural log of the bottom thing, minus natural log of the bottom thing. All the top factors get plus natural logs, all the bottom factors get minus natural logs. I'll say one more thing here, because there is another way you could approach this if you cared to. Instead, you could make the following choice, which I don't think is a bad choice. Or we could have rewritten f of x like this. It's the natural log of x to the fifth times e to the 3x times, if I bring that tangent to the fourth up to the numerator of the fraction, it's going to have a negative power. So it's tangent to the negative fourth power of x. Same thing for the x squared plus 2 to the 1/2. It's going to come up to the top as x squared plus 2 to the negative 1/2. And then you could do it like that if you wanted to. You can say that's going to break apart as natural log of x to the fifth plus natural log of e to the 3x plus natural log of tangent to the negative fourth of x plus natural log of x squared plus 2 to the negative 1/2. And then again, any power that's the power for the whole thing comes down. So we get 5 natural log of x plus 3x natural log of e minus 4 natural log of tangent of x minus 1/2 natural log of x squared plus 2. So if you want to do it that way instead, you'll still get to the same place. I don't like doing it this way. I don't know why. Really, like, there's no good reason not to do it this way. I just have a mental bias against it. But if you think this is easier to see than that, it's perfectly fine to do it that way. I should kind of circle back around and say the rules we're using to break this apart are the typical logarithm rules that say the natural log of a times b is equal to the natural log of a plus the natural log of b. The natural log of a quotient, a divided by b, is the natural log of a minus the natural log of b. And thirdly, the natural log of a to some power is that power times the natural log of a. Those are the log rules we're exploiting to simplify this before we differentiate it. That's the kind, so we'll come back around to this idea because there's another way this gets incorporated where it's terrible, where you don't start off with a logarithm. We're not quite there yet, but we're almost there. So let's look at a couple more examples. Sure. One that's a little bit less terrible. Let's keep things in order here. Sorry, I've got stuff all over the place as usual. Let's say we want to find for y equal to, excuse me. I want you all to try this one. The natural log of x squared times secant of x. I want you to first break this. Oh, question. Sure. Yeah. No, you're good. No worries. So I want you all to first simplify this doing two things. Break it apart into two logarithms, and then whatever powers you can bring down those powers before you take any derivatives. So here are the steps I would take. I would break up the natural log of x squared times secant as the natural log of x squared plus the natural log of secant of x. And then before I took the derivative, even though you could probably do it here just fine, I'd much rather bring this 2 down in front. You'll still get the same result if you don't, if you use the chain rule correctly, but I'm trying to not use the chain rule if I can help it. So I'm going to write this as y equals 2 natural log of x plus still the natural log of secant of x. I should also mention that if you're simplifying, that's the only thing you should be doing. Even though this didn't change from here to here, we can't start taking the derivative of this piece yet since we're still simplifying that piece. So either simplify or differentiate in the step. Don't try to do some of each. And then our derivative is going to be 2 times the derivative of the natural log of x is 1 over x plus the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of secant of x is secant of x times tangent of x. I will again point out here, you could simplify that last part, even though I said we usually know, the secants would cancel, and you could just say the last part is tangent of x. So if you really wanted to rewrite this as simplified, you could say it's 2 over x plus tangent of x. Let's see. Probably, yeah. Yeah, I do want to go about that. Cool. All right, so that's that's a lot of what we do with logarithms is you just take derivatives of functions with them in them. But we also use them to make it easier to differentiate more complicated things. Specifically, what I mean is things where you have a variable in your base and in your exponent. So for example, I want to find dy dx for the given function y equal to, let's make it, I don't want to do the one you probably all are going to see or are going to see. So let's make it a little more interesting. Let's say it's x to the power of cosine of x. And the problem here is it's not a power function, right? We don't have x to the third or x to the seventh or x to a number. And it's also not an exponential function. We don't have 2 to the x or 3 to the x or 5 to the x or 5 to a variable, right? We have variables in both the base and the exponent. So when this is the case, we apply what's called the process of logarithmic differentiation. I saw one of your instructors, I don't remember which one, I think it was Al, but I'm not sure, did show you kind of a formula for the derivative of f of x to the g of x power. No one should remember that formula. I don't remember that formula, and I've looked at it many, many times. The better thing to do, and I certainly will say, I don't think he said to memorize it. I think he showed it to you, and then still, every time he did a derivative like this, used the process. So don't memorize that formula. Remember the process of what we're going to do here. So the first step is going to be, if you see a variable in your base and your exponent, take the natural log of both sides. Now, most people aren't cool like this. Not cool, cruel. But someone wrote this as find the derivative of x to the cosine x. Before you can apply the process of logarithmic differentiation, you have to make an equation out of it. You have to make it as y equal to x to the cosine of x, so that then you can take the natural log of both sides. But you have to be able to take the natural log of both sides of this equality before you can do the rest of the process. Yeah. Yes, I was just about to. In fact, it was on my mind. I was like, gosh, it doesn't for him. There you go. So here's our equation. And the first step is to take the natural log of both sides. I want to remind everybody, we're not multiplying by the natural log. We are doing the natural log function to both sides of this equation. It's like taking the square root of both sides or squaring both sides. You're saying we're doing the same thing. And then the second step is to use the log rules to bring that power down in front of the natural log of x. So we can rewrite this as the natural log of y equal to cosine of x times the natural log of x. And now we're in a spot where we can take the derivative of both sides of this equation. So, in fact, I'm gonna write the steps up here. So take the natural log of both sides, bring down the power, fight the power. And then in the next step, differentiate both sides. Now, I'll remind you, just like what we started off with class today, if we have a function of y, we're not just pretending, we know y is a function of x. So if you've got something with y in it, you're going to have to use implicit differentiation when you differentiate that part. So the derivative of the natural log of y is going to be 1 over y times the derivative of y. On the other side, the derivative of cosine of x is going to be, the derivative of the product, and it will almost always be a product, because you're going to have that variable thing as your power that came down in front, multiplying by the natural log of the other variable thing that was your base. So it's always going to be your power times the natural log of your base, and those two things are both functions of x, so it's almost always going to be a product rule. There are some exceptions depending on weird things, but most of the time it's this. So we're going to use the product rule. It's going to be the derivative of cosine, which is negative sine of x, times leave the natural log of x alone, plus, now we leave cosine of x alone, and multiply by the derivative of the natural log of x, which is 1 over x. That was differentiating both sides. And I should say, on the left-hand side, when you do this, if you started with natural log of y, which is almost always what you're starting with on the left-hand side, the next step you're always going to get 1 over y times y prime. It's just going to be the same thing every time you do this. So then we're going to solve for y prime. So the first step is to multiply both sides by y. So we're going to get y prime isolated on the left equal to y times all the stuff on the right. You can simplify it a bit, although there's not a lot to do here. The only real simplification, I think, is to write cosine x times 1 over x as cosine of x divided by x. And then finally, since our y originally was a function of x, this is kind of always true. If you start off with y as a function of x, we should be able to write our derivative solely as a function of x. We shouldn't have any y's in it at the end of the day. And we can certainly fix that because we can replace y with what y is equal to, x to the cosine x. So I think you can kind of skip step 4 if you're comfortable with that and go straight to the last step here, which is saying that y prime is equal to what y was, which is x to the cosine x in this problem, times all of that. Negative sine x times natural log of x plus cosine of x divided by x. And that's our final answer. And I guess I can say so. Multiply both sides by y. And then we replace y with the function it's equal to. That is the process, and it pretty much never changes. A couple things I want to point out about this. I would always use this process for variable to a variable, but you can actually use it for other things as well. And in fact, I definitely saw in someone's lecture notes, they use this process for differentiating a really gross looking quotient or fraction. Or maybe it was either in the lecture notes or one of the homework assignments, I don't remember which. But so sometimes people say to use this process even though you aren't starting off with something like this. Let me show you what I mean. We'll do another example, and then I'll have you guys try one on your own. So someone could say, well, that was try and put numbers on here. That was number 5, sorry. Number 6. Someone could say find dy dx for y equal to x cubed times the square root of x squared plus 1 over sine of x times the cube root of x plus 2. And if they just said that, you could certainly do this one way. I don't even want to say the hard way because they're both kind of terrible. You could certainly differentiate this by using the quotient rule, and then for the derivative, the top and the bottom, you have to use the product rule for each of them, and there's probably a chain. It's kind of terrible to do this long. So they could say, find this derivative using the process above, logarithmic differentiation, even though it is not absolutely necessary to do so. So, first of all, we're going to take the natural log of both sides. So the natural log of y is equal to the natural log of all of that. And again, I do think it's a good idea for these problems to write any root as a fractional power. So we're going to write this as x squared plus 1 to the 1/2. And on the bottom, we have sine of x and x plus 2 to the 1/3. Okay. So now, the whole reason we've done this is to make the complicated side simpler. So unlike the previous one, we have a lot more simple. We're not just bringing down the power here. We're going to break this up like that other terrible problem we had. So we're going to have the natural log of y equal to, so watch this first step that I'm going to do. I'm going to skip a step here. In fact, I'll leave myself space to fill it back in. The step I'm going to skip is going to be the natural log of x cubed plus the natural log of x squared plus 1 to the 1/2 power minus the natural log of sine of x minus the natural log of x plus 2 to the 1/3. And as I said before, all the factors in the numerator get positive logarithms of those factors. All the factors in the denominator get negative logarithms of those factors. Totally fine way of doing it. Or if you wanted to, we could have taken an intermediate step of rewriting it as the natural log of x cubed times x squared plus 1 to the 1/2 times sine of x to the -1 power times x plus 2 to the -1/3 power, if you want to write it like that. Doing it not the way I usually would prefer to do it, but fine. And then it would certainly break apart like this. And then we can bring all the powers down and say that the natural log of y is equal to 3 times natural log of x plus 1/2 times the natural log of x squared plus 1 minus the natural log of sine of x minus 1/3 times the natural log of x plus 2. And now finally we're ready to differentiate both sides. So the derivative of the left-hand side is going to be 1 over the stuff times the derivative of the stuff. The derivative of the right-hand side is going to be 3 times 1 over x plus 1/2 times 1 over x squared plus 1 times 2x minus 1 over sine of x times cosine of x minus 1 over 1/3 times 1 over x plus 2 times 1. Unfortunately, unlike the previous logarithmic differentiation, well, no, unlike the other terrible problem with the quotient and the multiplication, we're not done yet. We have to multiply both sides by y and then replace y with what y is equal to, which is a little bit gross. I think I am going to do it just in one step. So we're going to say that y prime is equal to y, which is all that. So it's my x cubed square root of x squared plus 1 over sine x times the cube root of x plus 2. That's the y that we just multiply both sides by to get rid of it on the left, times all of that. And if I have to rewrite it, I am going to simplify it. So instead of writing 3 times 1 over x, I'm going to write 3 over x. Plus, instead of 2x times 1 over x squared plus 1 times 1/2, the 2's cancel, and I get x over x squared plus 1, minus cosine over sine is cotangent, minus 1 over 3 times x plus 2. They're not terrible simplifications to do, but since I'm writing it again, I'd rather write it as kind of simply as I can. Okay, so we're gonna kind of move away from this for just a second. We'll come back to it in a minute. So now let me finally get back around to answering the question that was asked about how do we take the derivative of some other power, some other base to the x. So let's say, for example, we wanted to find the derivative of 4 to the x power. Well, I'm going to show you two ways to do this. One way we already did it. Last time we talked about this, which I don't remember when that was exactly. We talked about how you just rewrite it as the derivative of e to the natural log of 4 to the x power. Not the way I like to do it, actually, but it's fine. And then that's going to be the same as the derivative of the x can come down in front of the natural log of 4 and say it's e to the x times natural log of 4. And now we have a thing we're used to seeing, the derivative of e to the stuff. And we know that the derivative of e to the stuff is going to be e to the stuff multiplied by the derivative of that stuff. So that's going to be e to the stuff. And what's the derivative of x times the natural log of 4? Well, we did this last time. What's the derivative of x times 7? 7. What's the derivative of x times 5? what's the derivative of x times any constant? Just that constant. Natural log of 4 is a constant. So the derivative of x times that constant is just that constant. In the other problems we did, we had to use the product rule because it was like x times the natural log of something with x in it. Here we don't have to use the product rule. It's just x times a constant. The derivative is the derivative of x, which is 1 times that constant. And then we're going to do one more thing. We're going to remind ourselves that e to the x natural log of 4 is the same as 4 to the x. Those two things are the same thing, just written differently. So I'd really, really rather write this as 4 to the x times the natural log of 4. Let's do one more, but let's do it a different way. I want to find the derivative, dy dx, of y equal to 6 to the x. Now, looking at our previous answer, we should all have a pretty good guess of what the answer is going to be here. Instead of 4 to the x times natural log of 4, I'm expecting to get 6 to the x times natural log of 6. But now we're going to do it using the process we just learned about, the logarithmic differentiation process. So we're going to take the natural log of both sides. Natural log of y equals the natural log of 6 to the x. And then differentiating both sides, on the left-hand side, 1 over our stuff times the derivative. Oh, I skipped a step. I needed to simplify this as x times the natural log of 6 to make my life better. So now, differentiating both sides, meaning this side and this side. On the left-hand side, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. On the right-hand side, well, again, the derivative of x times a constant is just 1 times that constant. Or just the constant. Finally, solving for y prime, we get y prime equal to y times the natural log of 6. So our derivative is going to equal, well, replacing y with what it's equal to, we're going to get 6 to the x times the natural log of 6, as we expected. It's a totally different way of going about finding it. Both are valid, both are good, they both got us the right answer. So just to kind of, yeah, we should do that. I got time, yeah. Let's see. Let me hold off. Okay, sorry, I'm just trying to think about what I want to show you. So, what I would say is, if your base is constant, you shouldn't use either of these processes. We're using them to just kind of show us what we get, but now I'm pretty sure that no matter what constant I have, I'm just going to get that constant to the x times the natural log of that base. So we could say that the derivative of e to the x is e to the x, and more generally, the derivative of some base to the x power is that base to the x times the natural log of b, whatever the base was. And we also have chain rule versions of these. We know that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And similarly, it's not a stretch to make the guess that the derivative of some other base to the stuff is also equal to that base to the stuff times the derivative of the stuff times the natural log of the base. You know what's really funny? Maybe not funny, but interesting, worthwhile is you don't actually need this first formula. A second formula is good if your base is e, because if your base was e, the derivative of e to the x would be e to the x times the natural log of e, and the natural log of e is just 1. That's why it's called the natural base, by the way, because it's the one where things like work out nicely. It is the natural base e, because when you take its derivative, things are nice. If we use a different base, things are less nice. I would say leave yourself some space down below here because we're going to come back. Well, in fact, we're going to fill in some logarithm rules. So we're going to say also the derivative of the natural log of x is 1 over x, and the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then in a moment, we'll come back and fill in the last line, which is log with a different base. So, yeah, leave yourself some room, James. Okay, sorry, now this went real fast. So let's look at a few more examples. Where'd you go here? Sorry, I want to make sure. Yeah, not that yet. Sure. So just to make sure we're cool with this, if I wanted to find, say, the derivative of 2 to the x cubed minus tangent of x, I don't want to go through the process of rewriting this in a different way. You can, right? We certainly could. But what I really want to know is, okay, the derivative of 2 to the x is 2 to the x times natural log of 2. So the derivative of 2 to the stuff should end up being 2 to the stuff times the derivative of the stuff. That's going to be 3x squared minus secant squared of x times the natural log of 2. Why don't you all try this one? The derivative of 4 to the x to the 5th plus sine of x. Oh, can someone make sure the sign sheet gets around over here? Thank you. One thing that I really like about these exponential functions, where you have a variable in your exponent, is it always shows up again. They're kind of special that way. Whether it's 2 to the something, or e to the something, or x to the something, or a variable to something, right? Even in those weird ones where you use logarithmic differentiation, the original function you started with always shows back up again as itself, unchanged. So the derivative of 4 to the stuff is going to be 4 to the stuff gets to show up again. And then we multiply by the derivative of the stuff. That's 5x to the 4th plus cosine of x. And we also multiply by the natural log of the base, natural log of 4. Order doesn't matter here. I prefer to think of the changeable part first and then the natural log of the base at the end. But you could have written 4 to the x to the 5th plus sine of x times natural log of 4 times 5x to the 4th plus cosine x if you want to write it that way. Either way is fine. So now the reason we're kind of actually talking about this is so that we can then say, well, what if I want to find the derivative of y equal to log base 3 of x? Ooh, different base for the natural log. From the natural log, not the natural log, log base 3. Here's what I would like us to think about. Well, this function is almost the same as the natural log of x, right? Exponential functions with different bases are similar. Logarithmic functions with different bases are also similar. They just look a little bit different, but still pretty much the same. So we would expect the derivative to pretty much be the same. We know the derivative of the natural log of x is 1 over x. I'm pretty confident the derivative is going to be 1 over x times something. And it is. Here's how we're going to do it. We're going to rewrite it. We're going to rewrite it as an exponential equation. So if log base 3 of x is equal to y, that means we have 3 as our base to the power of y equal to x. And now we're going to differentiate both sides of that because we know how to differentiate a different base to a power. We just did it. So the derivative of 3 to the x would be 3 to the x times the natural log of 3. The derivative of 3 to the stuff, just like the derivative of 4 to the stuff, is going to be 3 to the stuff times the derivative of the stuff times the natural log of 3. Or we're using implicit differentiation here. So when we differentiate both sides, we're going to get the derivative of 3 to the y is 3 to the y times the derivative of y times the natural log of my base 3. And on the right-hand side, kind of boringly, the derivative of x is 1. And now we're going to solve for y prime. So y prime is going to equal 1 over 3 to the y times natural log of 3. But we're going to write things in terms of x because x is equal to 3 to the y. So we're going to replace our 3 to the y there with an x. So we're going to rewrite this as our derivative is equal to 1 over x natural log of 3. So in a kind of nice way, a comparable way, when your base is different in an exponential function, like 2 to the something or 4 to the something, we multiply by the natural log of that base. When our base is different for a logarithm, we end up dividing by the natural log of that base, right? We're dividing by natural log of 3. Over here, we were multiplying by the natural log of 4. And that's very consistent. So if I was to ask, say, to find, sure, the derivative of y equal to log base 5 of x to the 4th plus 1, well, instead of doing the same process, although we could, and I think I probably will actually, I'm going to apply the more generic kind of rule, which says if the derivative of the natural log of x is 1 over x, and the derivative of log base 3 of x is 1 over x natural log of 3, then the derivative of the log base something of some stuff, I should be able to use the chain rule and also toss in the natural log of 5 where it needs to be. So here's what I'm thinking. I have log of some stuff. I don't care about the base right now. I'm ignoring the base. I'm saying, okay, the derivative of log of some stuff is 1 over the stuff times the derivative of the stuff. And then I also have to divide by natural log of 5 or multiply by 1 over natural log of 5. Yes, this is the worst way you could possibly write it, but that's okay. If you wanted to, you could certainly simplify this as 4x cubed over x to the 4th plus 1 in parentheses times natural log of 5. So to fill in the rest of that little kind of list of derivatives of exponential functions and logarithmic functions, here's what we have. Sorry, this is awkwardly placed here. Yeah, that kind of works. So we had the derivative of the natural log of x is 1 over x, and now the more generic formula is that the derivative of log base b of x is not just 1 over x, it's 1 over x natural log of b. Almost the same formula. You're just tossing in an x for natural log of b in the denominator. And similarly, the derivative of log base b of some complicated stuff is going to be 1 over the stuff times the derivative of the stuff. And then at the end of the day, we have to also divide by the natural log of b. And yes, you can put that all together in one thing. I just don't usually do it that way because I like to think of it in 3 separate pieces. That's tricky. Okay. Let's do a couple more examples here and then we will move on. So let's say, yeah. Where'd you example I had in mind? In fact, yeah, I want you all to try. We'll do one more. So let's say we want to find the derivative of log of, where'd you go? Sure. X to the 5th over cotangent of x. I should not use the quotient rule ever in this problem. I could, I shouldn't. I should simplify this first. So whenever you see log of something complicated, whether it's log base e or log base 5 or log base 10, which is what I have here, I should break it up if I can into smaller, simpler logarithms. So we're first going to expand this and write it as still the derivative of, because we haven't taken it yet, log base 10 of x to the fifth minus log base 10 of cotangent x. I'm not writing base 10, but I am saying it in my head. And now I could do, what else could I do here that I probably should do? I could also bring down that 5 in front. If you forget to do that, it's not like that vital, especially if it's x to the fifth. If it's something more complicated to a power, though, it really is kind of vital. Here, if you didn't do it, your derivative would be 1 over x to the fifth times 5x to the fourth, and then the x to the fourth would cancel. But it's better, I think, to rewrite it as the derivative of 5 times log of x minus log of cotangent of x. And now we're ready to take the derivative and get, all right, the derivative of 5 times some stuff is going to be 5 times, well, the derivative of the log of x is 1 over x times the natural log of what? What's my base? 10. Minus, okay, derivative of the log of some stuff is going to be 1 over my stuff times the derivative of my stuff, which is negative cosecant squared of x, times a 1 over natural log of 10. Or if you wanted to, you could slip in the natural log of 10 over here in the denominator, which I'm going to do. So exponential functions with different bases, we multiply by the natural log of the different base. Logarithmic functions with different bases, we divide by the natural log of the different base. Oh, where was I? Sure. So I feel like we didn't get to spend quite as much time as I wanted to on the process of logarithmic differentiation, which I did see, I think, on both practice exams I saw. Definitely on Alameda's, I think it was on the other one as well. So let's do 2 more, because there's one that I think is super funky that I want to show you. But let's try this one first. So let's say we have y equal to sine of x to the x to the fourth power. And we want to find the derivative. Find y prime. And I see the telltale hallmark of I've got a function raised to a power of a function. I have to use logarithmic differentiation. There's no other way of doing this. So we're going to first take the natural log of both sides. Okay, everybody else, write down the next step for me. Next step, we should have something times something, and we are bringing down the x to the fourth and getting x to the fourth times the natural log of sine of x. All right, we're now in a position where we can differentiate this. We can take the derivative of both sides. The left-hand side, as usual, is going to be the derivative is 1 over my stuff times the derivative of my stuff. The right-hand side, product rule and chain rule. Do it. So the right-hand side derivative should be 4x cubed times the natural log of sine x, plus then we switch which one we leave alone and which one we differentiate. X to the fourth times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. 1 over sine times cosine. Now I will say, I really do encourage, if you're comfortable with it, to do the next 2 steps in 1 step. I think it's a lot of writing, is why I don't think you should do both steps here. I would skip writing y prime equals, in fact, I'll do this instead. I would skip writing y prime equals y times all that stuff and go straight to rewriting it as y prime equals sine of x to the x to the fourth power times all that stuff. So my end answer is going to be y prime equals y, which is sine of x times x to the fourth. See, remember how I told you the original function always shows up? If it's an exponential thing, it's always showing up, right? Our original function is showing up in our derivative, and that's always true for any sort of exponential function where you have a variable in your exponent. This technically isn't an exponential function, but close enough as far as we're concerned. Times all this stuff. So it's going to be 4x cubed times the natural log of sine of x plus, I would simplify this as x to the fourth times cosine over sine is still cotangent of x. All right. No one's kind of, I don't know. Not the one we just did. The next one again, like that doesn't seem too useful. Oh, okay. So a question for you all. Has anyone's instructor talked about taking the derivative of the inverse tangent function or the arctangent function? Okay, not yet. It probably will come up after your midterm. It is something we do use in 17B, so we'll talk about it then. But yeah, because there's this whole theorem about taking derivatives of inverse functions, which is kind of weird. I won't lie. I've always thought it was kind of a weird theorem, but it does make sense. It's just I don't think we should talk about it yet. That's I think all I really had to cover today. We could keep going with something else, but I should pause and say, so I've got both of these practice midterms from your various instructors up here, which cover kind of all the stuff since the last exam. So let's give ourselves a quick reminder of what's going to show up on this exam that you're all taking next week. Let me click the button off there, sorry. So, and also I'll point out all the practice exams for both professors are posted on Canvas. I don't think Professor Xu, I think that's their name. I don't think they have, did they give a practice exam the first time around? No, so I wouldn't expect one the second time around. So luckily there's other stuff on our Canvas you have access to practice with. But let's kind of briefly mention like what content are you responsible for knowing on exam 2? So I can practically guarantee you're going to have to find the derivative of some function using the limit definition. Like, I would bet you lots of money that'll be on all of your exams. It's very, very, very unlikely that it will not show up. And looking at kind of what I'm seeing here, a couple examples I see of this on your exams are functions like f of x equal to the square root of 3x. What do I see on this other one here? Just to kind of see what kind of variety we've got. Usually the first question as well. Ooh, come on. Or on this one, or f of x. This one's kind of gnarly. 1 over x squared. There's one other one I had here. Sure. Or f of x equal to the square root of 2x plus 1. You're usually not lucky enough to get one that's just a polynomial. Like, it would be really, really wonderful if they gave you something like f of x equal to 3x squared minus 4x. So any one of these is totally valid, could be asked on your exam, very, very likely. Should we do one? Okay, let's do one of these square root ones. I feel like the square root ones are usually the weirdest. So we'll come back to that. So let's say I want to find f prime of x for f of x equal to, we'll say the square root of 3x plus 2, just to make it more fun, using the limit definition. And I think Alameda gives it to you. I don't know if Zhao does. Doesn't appear to. But again, this is just a review, so I don't know what he'll give you or won't. So I would start off by writing this every time. The derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Unless it was already written for you. But if it's not written, write that down. It shows the person grading the work, at least you know the definition. And then we start actually doing things. So we're going to write the limit almost every step here until we get to like the very end. So my f of x plus h, if it helps, and I think it does help, I like to, underneath my f of x, okay, well then f of something else is going to be the square root of 3 times something else plus 2. Right? Instead of writing in x, write parentheses. And then what goes in the parentheses? Oh, it's x plus h. So then when I write out my limit of my difference quotient, it's going to be on top the square root of 3 times x plus h plus 2 minus the square root of 3x plus 2, all divided by h. When we're subtracting square roots, we know what we got to do. We got to multiply by the conjugate. So I didn't leave myself enough room to write it over here, unfortunately, so I'm going to write it all again. So I'm going to do one tiny simplification here. Yeah, I do think it's worthwhile. So instead of writing 3 times parentheses x plus h, I'm going to write 3x plus 3h plus 2 minus the square root of 3x plus 2 all over h. And we're going to multiply that by the conjugate, the square root of 3x plus 3h plus 2 plus the square root of 3x plus 2. And we can't just multiply by it on the top. We also have to multiply by it on the bottom. Okay. So now, whenever you're multiplying by a conjugate, whichever things are conjugates, we actually want to multiply out. Whichever things aren't conjugates, we want to leave as just the thing times the thing. So in the denominator, we're going to have h times the square root of 3x plus 3h plus 2 plus the square root of 3x plus 2. Also, we know we don't want to distribute that h there because we know that our ultimate goal is to make that original denominator h cancel out. That's what we're trying to make happen, so then we can plug in 0 for the rest of the h's and not be dividing by 0. So we want to make that guy go away. On top, this square root times that square root, well, they're square roots of the same things, so we're going to get the insides. 3x plus 3h plus 2. Just like the square root of 3 times the square root of 3 is 3, or the square root of 9. The middle parts cancel. That's why we're doing this. That times that, minus that times that, adds up to 0. And then finally, and this is the part where it's really, really easy to make an error, which will make it really hard, we get minus parentheses 3x plus 2. We need those parentheses so that the minus sign distributes to the 3x and to the 2. Because we need all the not h things to cancel out in the top. And if you have 2 here plus 2 here, that adds up to 4 and is not going to go away. We need 2 here minus 2 there. So we end up getting the limit as h approaches 0 of 3x plus 3h plus 2 minus 3x minus 2 over the same denominator. I should say the same denominator as in the previous step. And now we can say, oh yeah, 3x minus 3x is 0. 2 minus 2 is 0. That's why we really needed to distribute that minus sign. And then I probably write too much with these problems. Honestly, like we probably could have skipped that step and gone straight to saying, yeah, we know the 3x and the 3x are going to add to 0 and the 2 and the minus 2 are going to add to 0. So we could have just had 3h and then said h divided by h is 1, and we're left with the limit as h goes to 0 of 3 over the square root of 3x plus 3h plus 2 plus the square root of 3x plus 2. Because what I'm doing here is I'm noticing, oh yeah, my 3h divided by h is just going to be 3. Finally, now that we have gotten rid of the problem h from the beginning, we can now plug in 0 for the rest of the h's. So we're going to get 3 over the square root of 3x plus 0 plus 2 plus the square root of 3x plus 2. And although we could leave it like that, it really should do one more thing. We really should say, oh, square root of something plus the same square root of something is 2 times that square root of something. So we're going to write this as 3 over 2 times the square root of 3x plus 2. And that's right. I wouldn't check it. I wouldn't go look at my original function and use the chain rule to take its derivative, even though we could. I would just say, looks good, good to go. As long as my algebra felt right along the way, I wouldn't check it. Unless you have all the time, like you've done everything else on the exam, you're like, okay, I wasn't sure if I actually did that limit definition one right. Let me go back and make sure the derivative actually is that, and then mess with it if it's wrong. But again, use your time efficiently, right? You only have, what, 50 minutes? Use it efficiently. Get as much on there as you can before you start going back and looking at things. I will point out, if you did check it, it is right. So if you just use the power rule to take the derivative of 3x plus 2 to the 1/2, your derivative is 1/2 times 3x plus 2 to the negative 1/2 times the derivative of the inside, which is 3, which is the same as that. It's just written a little bit differently. All right. So what else is going to be on your exam? Good question. Sorry, I know this is let me do this here. So limit definition of the derivative for sure. What else have we got here? So I would say basically so yeah, sure. Equations of tangent lines using slope and a point. So y minus y1 equals m times x minus x1. And typically you're finding the slope is the derivative of your function at the given point, x1 comma y1. So typically you'll find the slope by taking the derivative, plugging in your point, and then you'll find the equation by using your point, x1, y1, and your slope to find the equation. And then kind of broadly after that is essentially all the derivative things we've learned. So all the derivative rules. All the derivative rules and functions. Which I don't think we have enough space to write out here, but we have the usual kinds of things. We have the power rule, product rule, quotient rule, and everyone's favorite, the chain rule. You, I think, are expected to know all of these and to be able to apply them when appropriate. I guess there's also the constant rule and the constant multiple rule, but I feel like, sure, we can say those two. You should know the constant rule, meaning the derivative of a constant is 0, and the constant multiple rule, which is that if you have a constant times your function, the constant hangs out, and you multiply it by the derivative of your function, which we've done so many times. And then all the functions. So we have x to a power, e to the x, natural log of x, and the trig functions. Sine, cosine, tangent, cotangent, secant, cosecant. I think that's a pretty exhaustive list of all the derivatives you have to be able to, or all the functions you have to be able to find the derivative of. And looking at Zhao's sheet here. So I'm not sure if on this, so Zhao has given you, sorry, one second, has given you this kind of list of derivative rules. I imagine this is not provided to you on your exam. I wouldn't think that, unless I mean, it'd be nice if it was, but I don't think that's the case. Yeah, question. The constant multiple rule. So, and what that's saying here is that if you are taking like the derivative of, say, like 6 times sine of x, the constant multiple 6 just hangs out, and we multiply it by the derivative of sine of x, which is cosine of x. On the other hand, the constant rule would say that if you took the derivative of, say, like 6 plus sine of x, well, the derivative of 6 is 0, and the derivative of sine of x is cosine of x. So if you have a constant all by itself, its derivative is 0. But if it's multiplied by something else, it just sticks around. Yeah, okay, sure. And then where's the paper grip? That's right there. Wow, all of the place. Okay, as you. So after all the derivative rules and the functions, we talked about implicit differentiation. And I would point out there's usually 2 styles of implicit differentiation question. One style is given a terrible equation, find dy dx. The other style is given a terrible equation, find the slope of the tangent line or the equation of the tangent line at a particular point. And the difference between these two is, for this one, the first step is to differentiate both sides of your equation, and then do the algebra of solving for dy dx. So usually that means grouping your dy dx terms together on one side, and then you factor it out. And then you divide both sides by the leftovers, and you isolate dy dx. And the right-hand side plays out pretty much the same, except that when you're trying to find the slope of the tangent line at a particular point, you first differentiate both sides, and then you do yourself the favor right after that step of plugging in the point for x and y, not for y prime, right? Your y prime is still the thing you're trying to solve for. But then you'll do the same thing. You'll group the y prime terms on one side, add them together, and divide by the leftovers. So then the same. Group and solve. And then after that, we talked about related rates, which is the word problem. And honestly, the hard part about the related rates problems, I mean, the calculus is not super easy necessarily, but the hard part is usually setting up the problem. So working on the setup there is what's kind of vital. And then after that, we talked about exponential growth and decay. And then finally, the logarithmic differentiation that we talked about today. So these are the broad topics that are very likely to appear on your next exam. Practice, practice, practice. There's practice exams all over Canvas. You can email me if you have questions. I will make sure that I do get solutions posted to the one practice exam from Alameda from older that I don't have solutions for. So I'll write those up and get them posted certainly before Monday, probably before Friday. Meaning probably before Saturday, I should say. Yeah. So it's 1:27. I'll hang out for a few minutes if you have questions, but otherwise, good luck. So if you have your exam on Monday, good luck. If you have your exam on Friday, I'll see you a couple times before that. But we're probably going to start moving on because everyone else will have already taken the second exam. So yeah. All right. What's up? Sure. So yeah. So this is a graph of the derivative, right? So over here, the derivative is negative, so we know that the function is decreasing. And then here the derivative is positive, so we know the function is increasing.
We know the point is second.
We don't. We could totally shift this graph up or down. So one of the things about graphing the original function is we don't really know what the actual y values are. We just know what the behavior of the graph. So now right here, I don't know if it should actually look like that. What it should look like more is that it should look like more of an inflection point. So what I would say, where'd you go here? So if I was doing the problem, I would say, yeah. So I know that up until the order, so I know that my function's decreasing. And then from here to here, it's going to be increasing. But right here, that's going to be where it's increasing the most. Yeah, of course. So like it's going to do this. And right there is about like the steepest it's going to get. And then it's going to be less steep after that, but still increasing. Kind of like that. So right there, if I found the tangent line, it would be the steepest possible tangent line. And then same kind of deal from here to here. So now right here is where we're going to kind of max out. So again, we're flattening out for a second, and then we keep increasing. Very steep to right there, and then after that, kind of flattening out until we get to right there. Sorry, I should be there. We start decreasing like that. So what I'm looking at, right? So right here, so like right here, the tangent line should be a horizontal tangent line. Right here, the tangent line should be as steep as possible. Right here, the tangent line should be as steep as possible. And then right here, the tangent line should be 0. Right here, the tangent line should be 0. That's what I'm thinking about. You're welcome to take this. You can take it. What's up?
Not about like that.
Okay. Oh, well, let me do one thing. Sorry. Let me stop recording here so it starts compiling. Oh, the things in the chat. Sorry, one thing. Yes. Okay, yeah, go ahead.
So
In the summer? Okay.
And I already signed up for the work class.
Okay.
But we also do you put that foundation for the professor?
Do you know who's teaching it?
Yeah.
The Dell. That's what's up. So I would say students probably consider both of them to be challenging. I personally feel like Burke gives a little more support to the students. Both of them have high expectations. Dell often maybe teaches more content than is absolutely necessary. Whereas, yeah, I mean, I personally like both of them. I think they're both good teachers. I feel like I would probably choose to take Burke just because Dell's getting pretty old, and he's not as I mean I took him as an instructor when I was a student here in the year 2000. So, and he was not young then. He still knows what he's doing, but I just feel like he's a little bit less on top of it than he used to be. So I would say Professor or Instructor Burke, she's about my age, and they both care about student success. I think they're both good teachers. I know that students don't always feel the same way about them. Like I feel like they both get kind of they're right by professor pages, and the students give them a hard time because yeah. But I do really think like if you see either them in office hours or try to get help from them, like they do actually care about their students learning and succeeding in that. And they are both not professors, they're instructors, meaning their job is just to teach. So that's what they're doing. So yeah, I would probably pick Brooke just because I think she's a little bit she's got a little more energy, she's a little more with it. Dr. Adele is approaching 80 if he's not already there. So he's just a little bit less with it, I would say.
Okay, thank you.
You're welcome.